Alright, so the final type of application we're going to look at is a physics application. It's going to be modeling one-dimensional motion. We start with this example problem. And step 1 of our strategy says, familiarize yourself with the problem. So we read it. Kayla paddled for 4 hours with a 6 km/h current to reach their campsite. The return trip against the same current took 10 hours. Find the speed of Kayla's boat in still water. So we read it. We can read it again, take some time to absorb what we've read, and then take our pen and start trying to isolate the important information. So we have a 4-hour trip with a current of 6 km/h, and we have a 10-hour trip. Notice it is against that current of 6 mph, so with and against. It's going to look a little different. We will still do given and find, so we are given that the trip downstream, that is to say with the current, that took 4 hours. We have that the trip upstream, that is against the current, that took 10 hours. And that the current itself is 6 km/h. Okay, so and we are asked to find the speed of the boat in still water. I'm going to call that S. S for speed. Now, one of the things we haven't done yet in step 1, but could be part of step 1, is to go and look up some formulas. And we said on day 1, and some of you recognized it immediately, that we have a formula in physics. That is the distance, rate, time formula, and I said we would see that again. This, actually, would be very useful to us for this problem. Why? Well, we've got a rate, that's a speed, we've been given times, and we know the distance. We don't know a number for the distance, but it was the same distance in both directions, so I think we're dealing with a distance, rate, time situation. What we're interested in finding is the speed, which is a rate, so we can solve this equation for rate. I can divide both sides by t, and then rewriting that, rate is distance divided by the time. So that seems like it's something we should hang on to and might be useful to us. Another thing we can do, for those of you who are visual learners, is draw a picture. Physics is really good for drawing pictures. Physics problems make for wonderful art opportunities. I'm not an artist, so this isn't something that's going to go in the Louvre, trust me. But I can draw a little boat and our little friend Kayla. We can give Kayla a paddle. Pretend that's a paddle and not a very strange looking oboe. Here's our river. And if we are paddling with the current, well, we're going however fast Kayla can paddle, plus that extra 6 km/h, because that current is pushing us. So this would be our rate. The speed of the boat as Kayla pushes, and the extra oomph that we get from the current. We can draw a similar picture for the trip downstream. Oh, excuse me, that was downstream. For the trip upstream. The tough one. There's my river. Here's our friend Kayla going the other direction. There's their terribly deformed paddle. There we go. Maybe it's a shillelagh. And we are being pushed by the current. So we're saying, okay, assume Kayla can paddle at the same speed, even against this terrible current, Actually, that current is pushing against us. That would mean subtract, right? The total speed minus that current. That would be our rate for the upstream trip. So I can call that rate sub U. I could call this rate sub D for downstream. Or we could just keep using red and green. So all of this could be your step 1. And I said you can show work by drawing pictures as well. It helps, especially if you're a visual learner, to see sometimes. Right, so step 2 says let's translate this into math. Well, we kind of started that here with our picture, so we've kind of blended step 1 and step 2 a little bit. And we also have this formula. Well, we know R is d over t. We have R. We figured out that if we have Kayla pushing at some speed s, we add to that the current, at least for the trip where we are paddling with the current. And that is the distance, however far it is, from where they started to their campsite. And how long did it take them? It took them 4 hours. The second trip, well, we said that was s minus 6 because we are being pushed by the current. And in physics you will learn that the positives and the negatives are just a way of implying direction of force. And that trip took us 10 hours. We can clear these denominators to make our lives easier, which means we simply multiply by 4 and leave that there. And on this side we can multiply by 10. Okay. Equation 1, equation 2. We can move on to step 3, which says do the manipulation, do the solving, do the algebra stuff. We could use substitution or elimination here. Looking at this, I think I would like to use substitution. Notice that both of these are already solved for the distance d. So it would be very simple for me to just pick one of these up and slap it up into the other one. So 4s plus 6 equals d, but I have over here that d is 10 times s minus 6. Now I have a single linear equation in a single unknown. 4 times s, I'm just distributing the multiplication here and here. 6 times 4 is 24. And then 10 times s minus 10 times 6, which is 60. I can go either direction, but I would rather add the 60 to both sides. S, 6, 7, 8, that's 84, and that is 10s. Let's give ourselves some more space. Now I can subtract the 4s from both sides, giving me that 84 is equal to 6s. Last thing I want to do, divide by 6, and I have 14. 14 is equal to s. And the units on that are kilometers per hour. Okay. Now normally this is where we would back substitute in order to find the other value. But were we asked for the other value? Did we ask what distance we were traveling? No, we were interested in finding s. Now, if you had solved this another way and found d first, found a value for d, then yes, you should back substitute and find the value for s, because that's what we were looking for. But since we already have the value for s, we can move into our check. Nobody asked us what d was, so we don't care. So step 4 says check. And what we're going to do is go back to our original equations. S plus 6 should be equal to d divided by 4, and s minus 6 should be equal to d divided by 10. We have got 14 plus 6, d over 4, it's 14, 15, 16, 17, 18, 19, 20. 20. is d divided by 4. We can multiply the 4 over, and it's 80. And what we're going to look for now is to see that this also comes out to be 80, since they should be the same. Now if you had already found d and then back substituted for s, this check would look a little different. And maybe you do this a different way. But essentially we want to just confirm that they both give us the same distance. This is 8. That's d divided by 10, and if we multiply the 10 over, we do get that the distance is 80. So now we are satisfied that 14 kilometers per hour does work. So step 5, we write our conclusion. The speed of the boat goodbye. Or I should say in still water. Be very specific. Is 14 kilometers per hour. And yes, I would like to see units in application problems.